So, okay. So, we have had many questions, some of the issues we discussed, and we will continue it. So, let me go on, right, and we will continue discussing those points, because each of those points are quite involved actually, you know, we'll not finish discussion in 5 minutes, right. So, roughly this morning we finished at this point when we discussed what we call thermal equilibrium, right. So, we start with this equation. This is and S nu was equal to J nu by alpha nu, and we inferred that this would be 0. So, we have a geometry like this, we have some source emitting, we have another blob of gas in the middle, and we have a telescope right here. So, di nu by d tau, this would be 0, right. If this blob behaves like a black body, right, because this will equal this, but only under the condition that I nu becomes equal to B nu, and from this we derived a very simple relation, the J nu equals alpha nu B nu, which is actually a restatement of what you already know from your school. It's called Kirchhoff's law, right. Black bodies are those that whatever they emit, they reabsorb it, right. And this is actually a correct statement of what thermodynamical equilibrium means, which needs to be stated again, right. Thermodynamical equilibrium is one in which the matter and radiation are in equilibrium with each other, right. This does not mean they cannot be in equilibrium with each other separately. Again, now this is the important point here, right. And that is where all the microscopic processes come in, and I will have time to only touch upon a few of them, right. And I will introduce to you a concept of what is called the thermal source, where one of them is in equilibrium and the other is not. But this is a statement clearly that both of them are in equilibrium with each other, right. In that case, the radiation as it falls on it, there is nothing gained or lost from this blob, it just comes straight through it, right. No, it does not come straight through it because like there is nothing out there, there is a lot out here, but it has not actually got any net, right. Fine. So, one thing I will do before moving on is to show to you that just having a thermal source does not mean that radiation is black body. For that, I will go back to the solution I wrote, and please check this solution is right. I will assume the S nu to be constant. I had written an integral, remember? You might recall, go back to your notes, you will see that integral. I have just solved it by assuming that S nu can be pulled out, okay. Please check this is a solution. You should be able to check it readily, so that this is actually the solution. So, that integral can be integrated, say for a complicated source function, it is impossible to integrate it, right, because I do not know what its behavior might be, but suppose it is a constant, right. That means S nu is not a function of tau, right, it is a constant on this blob or maybe a column. So, this is 0, this is S. So, whatever is the source function inside of it, that means emission and absorption, they are constant, right, they are not a function of S along this length. So, I can pull this out and integrate that, okay. So, I have just done a few steps, but you should be able to replicate it without any difficulties, okay. So, this is the solution. Now, S nu I called was a source function that was written here, J nu by alpha nu, right. So, let us define a thermal source. If a source is thermal, so let us go back and ask ourselves what a thermal source is. Thermal source is something that is where the matter is in equilibrium, but if matter is in equilibrium, it must locally be interacting with radiation which is also in equilibrium, right, because if radiation was not in equilibrium, they will keep exchanging energy. If they keep exchanging energy, matter state will change. So, this is your first indication that that equilibrium one means equilibrium of another in some way, and has to be, right, but this is defined locally at a point. So, somewhere along the column I can define it, right. I would say that the source, the matter is emitting like thermally. This is called a thermal source. For a thermal source, S nu is B nu. I will replace it by B nu. This is black body. You will say, okay, this source locally, there is thermal equilibrium in radiation and matter, because without this equilibrium, it cannot be a thermal source, they will keep exchanging energy, right? But what does an observer see far away? Does an observer far away see a black body? Let's look at the solution of that problem, okay? And that will give us a sense, and that will give us a major insight into how we deal with things. Let's drop this for the time being. This corresponds to the radiation that is coming from behind, right? The radiation that coming from behind, we can drop this, right? So there is nothing coming from behind. Something is happening inside this body, right? And it is emitting towards us. There are two limits to it. When tau tends to infinity, I nu indeed becomes B nu, right? So it emits like a black body, right? But when tau tends to 0, for instance, I nu goes to tau nu B nu, it is not a black body. Is it a black body? Tau nu B nu is not a black body, right? Tau nu is a function of nu. This is a black body, right? So what we have found is the following. We have a thermal source locally, it is in equilibrium with radiation, but far away, the radiation that you observe may not be black body. Under one condition it is, under another condition it is not. Can somebody tell me what are these conditions, what is really happening? When tau tends to infinity, what happens? It's optically thick. Okay, let's ask ourselves the following question. Photon is coming from, can come to you from the entire column, right? It can come from here, it can come from here, it can come from here, correct? But if optical depth is large, is the photon coming from here? No, it's getting absorbed. It's not coming from here. Like I told you, right? The photon is internally absorbed, right? Is it coming from here? Nah. It's coming from here? No. It's actually coming right at the edge. The photon that you're receiving, and that was that integral which I showed you, right? That basically photon starts at some point, but then it's internally absorbed inside the column itself, right? It has to go that path, right? So tau tending to infinity means the following, that all the photons you are receiving coming very close to this edge, right? They are coming from one point, right? So actually this tells you many things. What the opposite case is also it tells you. What is happening in the opposite case is the following. This photon was B nu, right? Locally thermal equilibrium. So was this. But when it started to come towards you, it got absorbed. Fraction of it, right? Sure, right? It will get absorbed. Now what you see is the sum of the two. Sum of the two is not a black body. Remember, something that came from this edge was, but something that came from behind, it got absorbed, right? Coming towards you, part of it was absorbed. And it was absorbed preferentially at different frequencies, the absorption was different. Tau is a function of nu, remember? Which meant it's a sum of black bodies which are shifted from each other. Maybe it can be written as another black body, right? But it's not a black body. So it's not a mystery what is really happening. Black body is an abstraction that occurs when all the emission comes from one point, okay? And the best example of that is sun. You know how long does a photon that starts at the center of sun takes to emerge at the surface? Huh? It takes a long time, tens of thousands of years, right? I mean, these are just numbers. Actually, photon breaks into smaller frequencies and all. It doesn't retain its frequency, but it takes a long time. It's a classic case of an optically thick system, right? The photon that starts close to the center, right? The density of sun is close to the density of earth actually, pretty close. I mean, and you can see the mean free path of a photon you can compute, right? I mean, so it is a few centimeters and it actually has to random walk, right? Neutrino takes a few seconds to emerge from the center of sun to the surface because neutrino comes in a straight path. This photon has to random walk, right? And it takes 10,000 years, it's optically thick, right. So what we expect is the emergent light on the surface of sun is close to a black body, which it really is, except for the fact that there could be material after it has emerged in the, and that causes those emission and absorption lines, and solar spectrum is complicated, right. But one thing we have learned here is that even if the emitter is thermal, the light you receive from it may not have that nature. But under certain conditions, so this actually tells you a general condition under which the matter relaxes to equilibrium with radiation. There is one question you could ask at this point. When you derive the expression for B nu, which is going towards talking about source function, at that point you divide it by alpha, right. Alpha is a property of absorption, right. Does it not subsume the case of large tau? You understand what I am trying to say? See, the whole point is the following. I said tau is large and that is when radiation becomes black body. I said that, correct? Now you said, but when you define the thermal source, was that case already included in it? Maybe tau was large already to define even a thermal source, right? You can ask that question, right? I had to define a thermal source, right? When I made this identification, when I put S nu equal to B nu, was I not already, actually that's a very subtle point. And the subtlety of the point, first of all, you can see that that is not, because tau depends on the distance also, right? In this definition, there is no distance. So it depends on how far you go. Tau depends on distance, right? The other point which is actually happens in physics, and that is why we do this, is that matter relaxes to equilibrium with itself faster than photons relax to equilibrium with matter. These two time scales are very different, and that is why we have this condition. We would not have it. So that case would get subsumed in this. If that was the, I mean, under certain kind of matter, this would actually not happen. I will not be able to separate B nu from a black body, a thermal source from a black body. Both of them would be the same. But actually they are not, and it has to do with the fact that tau can be indeed small. Tau being small means the radiation can get freely through the medium, but the medium has relaxed to equilibrium with itself. The collision time scale between particles is much shorter than the collision time scales between particles and photons. Now this is again something, aim of my lecture is to give you an idea, you explore it on your own, right? Figure it out in more detail on your own, what I have just told you, right? Because I will not have time to go into this, right? But this is a very interesting and subtle point, right? How we deal with it, that we are able to define two equilibria separately, right? One just equilibrium of matter with itself, and another in equilibrium of radiation with matter. Do you think radiation can relax to equilibrium with itself without matter? Do you think that's possible? Yeah, how small? Actually, it's negligible. At small energies, it is actually zero practically. See, photons go through photons. It's only when the photons approach energies which are like the energies needed to create electron-positron pairs, only then they can actually scatter off each other. Otherwise, so photons do not relax to equilibrium with themselves. They need matter, but matter can, right? So you can have a thermal source which is not yet a black body, okay? So I think I've conveyed what I wanted to actually say, that there are two separate pieces and you have to study them in separation. At the other point that I was trying to make, I suppose that is well understood by this point, that because of this relation, if forward process is defined, so is the inverse process, right? Now I want to give you an illustration of that. Yeah, there is a question. Are there any questions at this point?
Sir,
yes, go on. No, I just said that, look, even if when tau is large, this will anyway go to 0, right? But I just said there is no background source. So you see, you can have a background source. So if you just want to like study what is happening inside of it, right, you can neglect the background source, okay? So you have that freedom, huh?
If we assume that tau is equal to 0, then there is no source for black hole.
No, tau is not 0. I mean, small.
It would be small.
Yeah.
Never 0.
Come on. So long as there is emission, there is absorption. Remember, this relation holds, right? You cannot have emission without absorption, right? They are related to each other, right? It's microscopic physics, right? So don't say 0, tending to 0. Then that means you're getting radiation from the entire column. And when the radiation is coming from entire column, like it cannot be black body, because you see it starts from some other point, part of it gets absorbed, so it's distorted, right? So you can actually do it like solve a differential equation and let tau go into larger and larger value, and you relax to equilibrium actually. You can actually see it yourself if you can do it numerically, right? By the way, yes, another question?
When
Yeah.
tau tends to 0, how can we say that I nu will tend to tau nu mean? I mean, can we say that from that equation?
Yeah, of course, from here, no? This is 0 anyway. When tau tends to 0, like it will be 1, this will be tau, right? 1 minus exponential of minus tau.
Okay, yeah, Taylor.
So I've just retained the first term, right? Yeah. So one thing before are there any other questions at this point? What about that exercise you gave in the morning? Everybody did it? All right, give me a sense of how you did it. One of you. 5 degrees he got. How about you? 8 degrees Celsius. Okay. I think all of you have made some mistake. Okay, one of you tell me how you did it, because somebody just showed it to me and he got 20.
I use the Stephen Boltzmann law.
Okay.
So the luminosity is 4 pi r square, the constant is sigma T power 4.
Yes.
The sun's luminosity is around 10 power 26 watts, and then the distance is 150 million kilometers.
And how much is intercepted on Earth?
So you do pi.
Okay, pi r square is good. Okay, so that is good. Good. Okay.
I didn't take that.
So you see your luminosity number is wrong actually by a factor of few. So I think you have not used accurate numerical values, right? You got 20, right? He even included an albedo, right?
250 Kelvin. Negative.
You got 250. No, some of your numbers are wrong. See, one thing is that one conceptual point here is how much energy is intercepted. That energy intercepted is by the area that sun sees, that is pi r square, but it emitted through 4 pi r square. So that if you got right, then there is but the entire, it's one fourth of power of the entire thing, right? So it's not very sensitive, but I think you have not used luminosity value correctly. No, it's okay. Albedo doesn't have, because you see, in addition to albedo, there is greenhouse also. That goes the other way. Okay, so there are all kinds of effects. I don't want you to bother about all of those effects, right? We still don't even understand those effects well, right? So, but okay, got 250. 250 is, you made a mistake in luminosity or distance somewhere, okay? So just check your numbers. See, there are 3 numbers here. One is the luminosity of sun, distance between sun and earth, and the radius of earth.
The radius of Earth cancels out, right?
Radius of earth will cancel out because of interception. So it doesn't depend on, so it just depends on luminosity of sun, the distance. So one of those things, he said 10 to the power 26, 10 to the power 26 is wrong. I think it's factor of 3 higher, the luminosity. Just check. So that is probably correct, the volumetric, that's roughly right from what I remember. What number did you get for? Check again. 255. See, 250, 255. You got 293, right? See,
Yeah, 281 something. 8 degrees.
people, you go back and so you see, conceptually, I think all of you have got it right. But numbers, I suppose some of the numbers you please check. Okay. I mean, Stephen Boltzmann constant, maybe those values you are getting wrong. Okay. Please check your number because that you need, right? So conceptually you got it right. The idea is the following, it's very straightforward. There is sun and earth intercept a part of that energy at every given time of the day and then re-releases it throughout the sphere, right? And that is the idea really, right? And so from sun's luminosity and the distance to it, we can compute the radius, and the radius of earth cancels out, as somebody pointed out. We don't even require it, we can compute the temperature. But some of those constants, if you got wrong, please check. 255, no, you will get around 20 degrees if I remember right. Around 20 is roughly right actually, okay. But that would be a slight underestimate, because I think greenhouse makes a bigger difference, and then there is albedo. There are all kinds of factors. It's a function of frequency, right? But you got the point, right? So I'm glad so many of you tried it. Everybody, the back door, you tried? You got something? What is this? All right, you check again. I mean, I'm not going to do it here, okay? You please check, go back and check those numbers, okay? You will get, I think, 30, 40 degrees more, okay? But conceptually you got it, okay? So I'm glad. So now we talk about something slightly different. Okay, you can check your numbers. Let me go on, okay? And so now I'll give you a specific implementation of what we were talking about, and we will discover another subtlety, okay? Of what is a thermal emitter, how do you approach black body, and what relation do you require between forward and inverse processes, right? That specific implementation is by Einstein, and he actually realized that there is a subtlety which is missed. In Kirchhoff's law, when I wrote it, you will immediately realize some part is missing in that. Even though it's formally correct, the absorption is broken into two pieces, and one of them is not absorption, it's emission actually. So what we do is we look at the two-level system now, right? So this has population of N1. Have you, quantum mechanics, everybody has done something? Basic course, right? So you are aware of all these two-level systems and all, right? So what we'll do is, the geometry that we have here, emission, then a blob of gas here, and then telescope here, this is a two-level system, right? So photon is coming from behind and it's interacting with a two-level system, right? And the population of the lower level is N1, the population of upper level is N2, right? And we will specifically analyze this case, right? So first, let me write a few things and I'll explain later. So if there are atoms in the excited state, right, then they will come to the ground state and emit photons, right, in your direction. So let me just give you a sense of how much is that number in terms of intensity. So emission is this. I'll go back to my earlier notation, ds I will write. Let me briefly explain what I have written just now. So what is emitted in your direction, so these are units of intensity actually, which you will struggle to find. That is proportional to the energy of the photon, which is h nu. It's an isotropic emitter, so 1 by 4 pi has come from that, right? It depends on how many atoms are there in the excited state, N2. It depends, now I have introduced a quantum mechanical factor here. This is called the A coefficient of the atom, and this is the rate at which the upper level decays. There is a rate at which the upper level decays, right? So how much you get depends on how fast the upper level decays. And there is this phi nu. Phi nu is a complicated factor, which is actually a normalized probability. This tells you the probability of emission at this frequency, right? The atom does not actually emit at a single frequency. Atom is moving, right? And even internally, because of Heisenberg uncertainty principle, it has a width. All those factors get absorbed in this normalized function called phi nu, okay? So this is what we get along the line of sight because of the decay of the upper level, okay? Fine. Now we go to the absorption part. Somebody should tell me how much the absorption might be. Minus, it will be minus. I nu must be there, right? These factors would be there, correct? N1 It will depend on n1. What is the population of the lower state, right? It will also have a phi nu. You may ask, why is this phi nu the same as this phi nu? Could not be different. But I will assume it to be the same for the time being and not go into this discussion. This discussion has this additional subtlety, but this can be assumed. It's not a bad assumption. Okay. Then another factor has to come which is related to the probability of absorption of the photon in the ground state, right? This I will call B12. Correct? You agree with me that this is a fair thing to do? It's a simple two-level system. This is emission into your line of sight. This is absorption from your line of sight. Whatever is emitted in your line of sight, this is absorbed, this is taken away, right? This is released. Now when you look at these factors, you can do exactly the same exercise you did, right? However, now you would expect that by putting di nu by ds equal to 0, you should be able to solve for I nu, and that should be black body. But first you say, okay, what is the equilibrium level population? What is the ratio of level population in equilibrium? Do we know that? You want to say something? So go on, please. It has to be, it is called spontaneous emission. I'm coming to that point. Yeah, that is the point I was trying to come to, right? So you have read it. Have other people been introduced to this idea of stimulated emission? You have heard about it. That's what I was going to come to. But I was going to derive it. I'll emphasize the need of it. So this is what is called spontaneous emission, right? But the point is really straightforward here, that if you, and this was known to Einstein, that in thermal equilibrium from statistical physics, the ratio of n2 by n1, which is the ratio of the population of the upper level to the lower level, is this. Where these are called the degeneracies of the level, the state. So in quantum mechanics, what you have is that when you call something a level, it can have other quantum numbers, right? So typically, for instance, in hydrogen atom, the n equal to 2 excited state has many states associated with it. So it has more degeneracy than the ground state, right? I will give you specific implementation of this in a short while, right? So this is G2 by G1. So this was known to Einstein, and there is one thing which is immediately clear to you, that if this is n2 by n1, right, di nu by ds equal to 0 does not give you a black body. B nu is not equal to a black body, right? I need one more term, right? And that one more term must be proportional to I nu itself, right? It should be equal to I nu, and it should be equal to n2, right? I will just write down that term. So I will include that term. Can you see where the problem is? From whatever we have learned, I should have derived B nu by equating these two, but I cannot, because n2 by n1 is given by just this factor, right? So this is not black body. There is an additional factor which you can easily derive actually what the additional factor would be, right? So this is called spontaneous emission. This is called absorption. And the third factor has come to be known as stimulated emission. So you see, Kirchhoff's law doesn't tell you about that. It hides it. It's there. It's not that it doesn't, it's not there, it's there in that formula. But it doesn't, it hides the fact that you need it, right? That there is one factor where emission is stimulated. By stimulated you mean, so let's understand what spontaneous emission means. Spontaneous emission means if an atom is in the upper state, it decays on its own to the ground state. Absorption means if the atom is in the ground state, it absorbs photon and goes to the excited state. Stimulated emission means if the atom is in the upper state, right, radiation falls on it and forces it to decay to the ground state. See, now that's a completely different process. That's the basis of what we know as lasers, right? Lasers like completely rely on the fact that there is stimulated emission, right? Because stimulated emission, it turns out, happens in the same state in which the incoming photon is. So you multiply numbers of photon in the same state, right? So in the same quantum number, if you multiply photon, that's how you get lasers, right? So I will write down the final equation. So that's a complicated thing. So there is a process which we never anticipated, but we are forced to include it again because thermodynamical equilibrium is expected. System will relax to equilibrium. If the particles are in equilibrium, radiation will be in equilibrium locally with it. And if that is the case, then we cannot avoid the conclusion that there has to be a third process, right? And that process, like I said, has to be proportional to I nu. If you are going to derive from this B nu, you can see that, right? So that process is light actually impinges on the upper state and forces it to transit. So it is stimulated emission. It is emission, but it has been stimulated, not spontaneous, gone.
I cannot understand how it can, some radiation can fall on the upper energy level and then come to the lower.
Yeah, but it sounds similar to absorption, right? Where the radiation comes and it absorbs.
Correct. I mean, why is it, yeah, why is it different from that? It is because you see, we think in a certain way, right? So I suppose like the way the language is used, that we think something is in upper state, so it can only decay spontaneously. Why? Actually, quantum mechanically, actually when you go back to quantum mechanics, spontaneous emission is far harder to understand than stimulated emission. Quantum mechanically, actually it makes much more sense to have stimulated emission from arguments of symmetry alone, right? When we start doing quantum mechanics, it is spontaneous emission which is actually a difficult calculation also. To compute spontaneous emission coefficients is harder, okay? So spontaneous emission, but you see our minds are like that. We think spontaneous emission, there is something spontaneous about it as our minds capture it, right? But no, it is actually what he said is correct. Just that absorption, absorption you didn't find surprising. Why stimulated emission? It's a similar process, right?
Sir,
Yes.
how did you get that ratio N2 by N1? I mean, equating that to 0.
Sorry, what about this?
N2 by N1 equal to G2 by G1.
Mm-hmm.
How did you get that?
Yeah, so this basically comes from Boltzmann law, okay. So this comes from Boltzmann law, which was known to Einstein by that time. So some progress has been made in statistical mechanics, and this was known to Einstein that N by N1 would be like this, right. So you have done this kind of calculation in a macrocanonical ensemble, right, you would have derived it, okay. So again 30 years before that he would not have got it. When Kirchhoff got his law, he could not have anticipated this, see my point. But by the time Einstein derived it, he could, because this is crucial to the argument, right. This is crucial to the argument that for one case we know it, right. Because when I do Bremsstrahlung, for instance, I do not have, I can't immediately guess that there will be a spontaneous emission, but stimulated emission, but first you pay attention to it, you will find that stimulated emission term is there, right. But here it's staring at your face, I can't get a black body by equating these two terms, right. These are what is called degeneracies. So when you actually share energy, right, when you share energy equally between different degeneracy state, right. So for instance, hydrogen atom, the p state, right, there are many p states, there is not a single p state, right. So photon has a certain probability of going into any of them. So energy is shared between different degeneracy. By this means by degeneracy I mean the energy state is the same, there is another quantum number, right, which gives it degeneracy, okay. So I will talk about one case, hyperfine structure of hydrogen, where G2 is 3 and G1 is 1, right. But I will come to that point. Let me go through this calculation, then I will come to that specific point where I will show you numbers. So when you include that term, this is what you get. This term we are familiar with. It is this term that has been introduced. see, this is it. You put the left hand side equal to 0, right. So, you see your equilibrium solution is I nu equal to B nu, correct. So, by equating these two, whatever relation you may imagine between B12 and A21, you will say A21 and B12 and the relation between them is not specified yet, right, but it will be a linear relation. You just can't get black body, right. So, what you need is another term, and then we define relations between different coefficients. There are 3 of them, right. The whole point is by equating these two, you just don't get a black body, right. I nu equal to B nu is not a solution to this problem. B nu is known to us, right. B nu is known to us. So, by introducing an additional term, which is this term, the second term of the equation, which is basically stimulated emission, it depends on N2, but it also depends on I nu. Again, I have assumed the phi nu to be the same for this, right. This is yet another assumption, but generally holds, right. Here now I will be able to get a black body, right, but I will have to still assume some relation. For instance, you will have to assume, yes, go on.
When you are introducing that stimulated emission,
Mhm.
you are keeping that notation same, only just interchanging the indices. So, then just notation or anything
Sorry, say it again.
that B1 to B21.
Mhm.
So, you are just interchanging the indices.
Yeah, because that's a notation in the literature. I mean, there's not, I did not devise it actually.
Yeah, I thought maybe emission or absorption.
No, so the point is B12 suggests this is a relation, something going from ground state to excited state. B21 is suggestive that is the other way around. B21 is the stimulated emission part, right, and B12 is the absorption part. So, this notation is common, right. So, there is a probability, so that additional term that we have introduced, it gives you the probability that a photon will hit the excited state and force and induce release of another photon by making the atom transit to the ground state, right. So, that is the new term that has been introduced, and I will just write down those relations that you may have seen already, and you can verify for yourself that this is indeed a black body in this case. If G1 B12 equals G2 B21, A21 it's a relation between B21. Yeah. If these relations hold, then the solution to this under the condition of thermal equilibrium, which is when N2 by N1 is given by that, B nu is indeed black body. You can check for yourself. So, this is something I want you to check. Put this equal to 0, just solve for the right hand side, right, what B nu is, right. So, I nu will become B nu in that case, right. So, it is this divided by this whole factor, use these two relations, and you will get from the numerator you will get 2 h nu cube by c square, which is, and the denominator will give you exponential of h nu by kt minus 1, right. I want you to go through this exercise yourself. All these h nu by 4 pi, all these factors and phi nu factors will all cancel out, right. So, this is equilibrium condition, but now we notice something more than what we saw before. There are two conditions now. So, there are no two coefficients, there is no forward process and inverse process, right. There are actually two, you can call it two forward process and one inverse process, right, or the other way around depending on how you want to define, right. Two things depend on N2, so maybe there are two inverse. So, one forward process and two inverse processes, right. So, now that is a very important thing, which basically means the following. Again, that to compute all three, I have to compute just one, right, and that is how it is done. For instance, for hydrogen atom, when we are trying to actually, if you want to know the probability of absorption in the ground state, right, I do not actually compute the probability of absorption in the ground state. All the thing, the only thing that is really computed is A21. A21 is computed, right. Once A21 is computed, all the rest of the quantities are here. You have to know the degeneracies of the respective states, right. So, typically what books will give you, quantum mechanics books will give you, they will always give you 8 to 1 factor, there will be a list, they will never give you B2, because this you can compute quite directly, right. You know how these are related to each other. So, this is not just about thermodynamics, this is about quantum mechanics, right. So, you may wonder, oh, why is it that probability of absorption is not given to you, because like I know I have given you the relevant quantity, you can compute the remaining, right. Is this point clear? So, this actually generalizes what we were talking about in the morning. The generalization is there is an additional physical process actually, which has to be taken into account, right. And that additional physical process, now once you know it, you would actually start finding it everywhere, that there is a stimulated emission that is happening. The role of stimulated emission is to lessen absorption. Can you see that? The role of stimulated emission is to lessen absorption. Okay. Absorption would be more without stimulated emission, right? Because some of the photons which would have, because without stimulated emission photons are not going to induce N2 to come to N1, right. So, I will give you an example, and for the remaining part I will give you a concrete example of hyperfine structure of H1 and put numbers so that you can appreciate what we are dealing with here. Okay. That is what I will try to do. So, I wanted to do something else, but I think I have time only for that much, but that I will do. So, let us try to see a concrete example and implement this, whatever we have discussed so far. So, hydrogen atom line structure is very complicated, right. This is n equal to 2, this is n equal to 1. The n equal to 1 is actually split by hyperfine transition. Have you heard about it? You have heard about it, right. A Feynman lecture has a full chapter on this hyperfine transition, right. This is spin-spin coupling, right. So, the ground state is split, and that this is called 21 centimeter line in astronomy, right, the famous 21 centimeter line, because that is the wavelength of the emitted photon, 21 centimeter. Frequency is 1420 megahertz. But let us look at the other quantities now, right. It is an extremely weak transition, right. But I can tell you one thing, the importance of this line is that if you want to see hydrogen in absorption, in emission, this is the only line that is available to you, right. All the other lines are so far above the ground state that they are hardly ever populated. This line is always populated. So, let me give you other numbers related to this line. G2 by G1 is 3 here. So, ground state of the hyperfine is a singlet, and the excited state is a triplet, right. And you can actually see this is S equal to 0 state, and that is S equal to 1 state actually, right, of that when you are looking at spin of nucleus, the proton and electron. So, these are the two states it splits into. S equal to 1 is a higher state, and that is a triplet. S equal to 0 is a ground state, that is a singlet, and the ratio of the degeneracy is 3. What is actually remarkable about this line is how slow it decays. Let me tell you the absorption, the decay constant for this, it is 2.85 10 power minus 15 per second. So, we are talking about 8 to 1, right. This is the rate at which this line decays. If you keep an hydrogen atom in the excited state, it takes roughly a few million years before it decays on its own, few million years, that is slow. Do you know what the A coefficient for Lyman alpha line is? This line, who said something? You are absolutely right, it is 6 into 10 power 8 roughly, sorry, per second, that is correct. So, these are, so Lyman alpha has, it decays 10 to the power 8 atoms per second decay from the excited state to the ground state. Here the atom does not decay for a few million years, the ratio between the two is 10 to the power 23. Okay. Now, this is basically again has to do with quantum mechanics, that one of them is what is called dipole radiation, classical dipole radiation, this transition, and this one is highly suppressed, is alpha to the power 6, it's highly suppressed for multiple reasons actually, this hyperfine transition, okay. So it has an extremely small probability of decay. So you may ask, this must be a weak line actually, right? How do we ever see this line? It does barely decays, right? If it doesn't decay, how do I see it? See, this line has an interesting history because this was actually first seen in space before it was seen in a lab on Earth. And the reason for that is that out in space, there are quite a few atoms, quite a few, galaxy has quite a few of them, okay? And the gas is very dilute. So this is not another atom that comes and hits it and takes away the energy, that also doesn't happen very often. So both those conditions are met in space easily. Of course, it has been seen in lab multiple times, but it was originally seen in space. This line became famous because of astronomers, the hyperfine line, right? And recently we went to a school in Gauribidnur. You people are going to visit Gauribidnur, right? Ask somebody to show you this line. They have a telescope which does this. You're taking them. See, okay, fine. So he's already set it up. Yeah.
Can you just why it is so hard to find this?
See, decay is very slow, right? If you put an atom, it takes a million years. Like you do an experiment in a lab, like you're not going to wait a million years for it to decay, right? So the only way to detect it is there are quite a few atoms out there, right? So in labs, it's harder to do that. In space, along your line of sight, you see, there is like 10 to the power 9 solar masses of hydrogen gas. That's all decaying. So that more than compensates for the smallness of this factor, right? So you are going to see this line. Like, so the whole point is an ongoing experiment out there and they will show you this line. And the complicated shapes that this line takes through the day, right? So when the galaxy comes in and it goes out. So you'll have real experience. So this is what this line is, very weak. Its A coefficient is almost 23 orders of magnitude smaller than a Lyman alpha transition, but this is the only way we detect neutral hydrogen, because you see it's so close to the ground state. To see neutral hydrogen, every atom is in the ground state, right? Now how do I detect something in emission? How do I detect it? It's in the ground state, I can't detect it, right? It's in the ground state. I must first put it in the excited state and then let it decay and then I observe it, right? Now when you put enough energy to put it to Lyman alpha, actually the ionization of hydrogen is just above it, right? You can check it. This is around 10.2 electron volt. Ionization is 13.6 electron volt, okay? So if you put enough energy to put it here, it mostly ionizes it. So you cannot actually do it. So the real way in which we have detected neutral hydrogen in the universe is all through by using this line. So it's an extremely important line. Let's look at what happens to this line when we take into account these processes, okay? So I'll keep this equation here and have this line in mind. Okay, other factors also of this line I have to put, no? Where I must have put it here somewhere. Yeah, here. Sorry, not alpha, sorry, 21. So this factor, see, I have to compute this exponent factor, right? So h nu 21 by k is 0.068 Kelvin. This will play a role in what I am going to say. Now what I will do is, I will define alpha the same way as defined by using this entire factor, absorption. Now absorption has part of it is emission, part of it is negative, part of it is positive, right? I will use this formula, right? And I will see what I get. But for these numbers, alpha nu h nu by 4 pi n1 b12 I will take out common, I defined this entire thing as alpha nu, the way I was doing in the morning, right? This is the absorption coefficient. So I will redefine it. I am defining a few quantities, like, let me do that anyway. Where sigma nu is called the cross section. It is I will not find values of these quantities. I could do that, but I am running out of time. So you can compute these cross sections and various things because you have all the relations with you. Once you have A coefficient, you have B coefficients, right? You know the wavelength of the emitted light and frequency of the emitted light. What I will try to focus is on one simple fact. What does the stimulated emission do to this process? Okay, let's just look at this. Okay, if stimulated emission was not there, this term, the term in the bracket would be unity, right? Correct? So then alpha nu is just equal to the cross section of absorption multiplied by the number density of atom in the ground state. Right? This is something we are familiar with. Let's see what stimulated emission does to it. Let's compute this. So you can readily compute this. Yes.
That sigma nu where why have you written phi nu?
It would be here somewhere, right?
Okay. Yeah.
Phi nu is here.
Yeah, because
So I forgot, sorry. I forgot in the definition of alpha. Right. Just check, you see, any mistakes that are remaining, you just check always the dimensionality, right? So phi nu is like when I was reading the board there, I made a mistake here. So sigma nu you can check. Sigma nu has what dimensionality? What are the units of sigma nu? Huh? Cross section. Meter square. So you see, you can see meter square for cross section, right? N1 m to the power minus meter L minus 3, right? Alpha has dimensions of 1 by length, right? This is dimensionless. So you'll get it right. So you would have got your phi nu because like phi nu has units of 1 by frequency, right? Phi nu d nu is unity, right? So you have to get it right. Okay, let's look at this factor. What is this factor? How much difference does stimulated emission make to absorption of the hyperfine line? So this factor, which is 1 minus G1 N2 by G2, is equal to, and you can check it readily, that you can check, right? Because of N2 by N1 we know is exponential of minus h nu by, and these degeneracy factors will cancel out, right? Now h nu by k I already wrote is 0.06 Kelvin. Anywhere in the universe the temperature is much larger, right? Typical temperature in our galaxy that you would see, what you will observe is around 100 degree Kelvin, right? So this factor is much smaller than unity. Okay, so this is on the order of h nu by kt, right? Correct? Yes? Here N2 by N1, N2 is G2 by G1 exponential of minus h nu by kt, right? And there is a G1 by G2 here, so they will just cancel out, right? These two factors will cancel out. Remember N2 by N1 I have erased it. N2 by N1 was G2 by G1, so that this is G1 by G2, they will cancel out. That's what I meant. So there are no degeneracy factor here, right? They go away. So now we can see what we have just done. Absorption without stimulated emission would be the cross section multiplied by the number density. There is an additional factor that is multiplying it, which is h nu by kt. And what kind of a factor is it? It's extremely small. It's much smaller than unity, right? If you take a typical setting in intergalactic medium, this will be 0.0681 Kelvin, right, 0.6, that was what it was, h nu by k, right, and divided by 100. Let me put a 7 here. So this is roughly 1 by 1000, right, even smaller than that, right. Point 0, is it okay? 0.07 divided by 100, I have taken a typical temperature to be 100 Kelvin, okay. So at 100 degree Kelvin, its factor is 1 by 1000. What does it mean? Now we actually are ready to see what it really means actually. What it means is that you have this atom, some photons are absorbed from the ground state and go up, right, some spontaneously decay, but there is this third factor, which is spontaneous emission. So of 1000 photons that are absorbed from the ground state, almost 999 are returned back through stimulated emission. See my point? So it is not a weak process, it is not a negligible process, it is an extremely important thing which you have to take into account, right. It is such a powerful effect that almost 1000 photons you absorbed, they do not go out because the point is from the excited state there is stimulated emission which puts it back again in your line of sight, right, which basically means that, and you know, in astronomy such atoms and molecules play an important role, and you can see what kind of atoms and molecules I am talking about, the ones which have a split very close to the ground state, where the ground state splits, okay, and ground state splits and the energy level, the energy difference is extremely tiny. In that case what happens is that stimulated emission cannot be neglected, it is not small, right. By the way, if it was for Lyman alpha line, there is n equal to 2 line, right, I plotted. For that h nu by kt, you can actually check if T is 100 Kelvin, h nu by k is around 10 to the power 5 Kelvin, okay. So this is negligible. So stimulated emission does not play a role for lines which are way above the ground state. Lyman alpha line plays no role, you can check, but the line, something that is very close to the ground state, I mean it actually weakens the absorption, and it weakens quite dramatically actually the absorption. So seeing a hyperfine line in absorption, knowing its emission properties actually is a test of quantum mechanics, right, because this is extremely weak, this is like not just a small factor, it is a huge factor. So it is actually a huge game to try to see these lines in absorption, and this is an ongoing effort, like many of our colleagues have done it using GMRT long ago they started, but of course telescopes all over the world have done this. It is all in radio astronomy, right. So this is one illustration of how when you take into account all the physical processes properly, it is not a small effect, it is a huge effect, right, and it is testable. It has other implications which I could have gone into, but I think I have run out of time. So I will stop now and then we can continue our discussion outside, right. So I cannot start anything new now at this point. So please go on, ask questions. See, the point I was trying to make is the following, that I just wanted to illustrate one point about this line, that we showed the following, that stimulated emission is needed, right, that is number one. If stimulated emission is needed, the next question was how important is it? Is it just of theoretical curiosity or does it play an important role, right. So I gave you one specific example of one of the most important line in all of astronomy, this is a hyperfine line, right, where stimulated emission actually plays an extremely important role. That is the point I am trying to make, right. No, 1 out of 1000, suppression is by a factor of 1 by 1000. So by a factor of 1000, it is a huge effect, it is not 1 by 1000, it is a factor of 1000 suppression, right, that is the kind of suppression that has happened. So absorption is certainly extremely weak, it would have been a powerful process, but it is extremely weak now, it is not powerful at all, right, and so this is something we see, right, even though astronomy has not been used yet to compute the quantum mechanics of this, but we see enough evidence of it when we are able to see line, H1 line for instance in both emission and absorption, right. I mean, but again I would not have time to go into it, I could have shown you some of those spectra, but some of those you would see when you go to Gauribandur. You would see absorption, this is also inversely proportional to temperature. So absorption is dominated by regions which are cool regions, and emission is independent of temperature. So you would see lines when you go there, you will probably pay attention. If you pay attention, there will be absorption within emission, you will see it, right. So pay attention. Now when you go to Gauribandur and somebody is trying to show you that line, you ask questions. Explain to me the complicated shape of the line, okay. The line would not be straightforward. It will be a complicated line because many of these factors are playing a role there. So all the best for the rest of your course. Okay, you have just come here a few days ago. So, and if you have any questions regarding any of these points, my office is next door, right. So please come by, okay. And one thing somebody asked me about, one reference for this, there is one book by Rybicki and Lightman. I will write the name, Rybicki and Lightman. It is called Radiative Processes in Astrophysics, okay. This book you should be able to download, okay, it is available. But what I suggest to you is what I suggest to everybody. You people are much better at looking at internet resources. Look for your own resources on internet. Don't rely on a book, okay. Even I do it these days actually, because you will have one question, then you have another question, and so it will go. You can keep searching and you will do much better, right. So rely upon your intuition. But if you want to start, you can look at this book. Yes.
Just to conclude, spontaneous emission is the reason for certain
Why do you say that? Why not stimulated emission? It's an equally important process. See, that's what I'm trying to say. Don't, these are words. As you yourself pointed out some time ago. Don't go by words. We have they are equally important processes. There is no difference between the two, right. It is the stimulated emission we find odd. Somehow we have this sense that stimulated emission is odd. But quantum mechanics actually treats it on par with absorption. So in fact, it is much more obvious that stimulated emission will happen in quantum mechanics. Then spontaneous emission will happen in quantum mechanics. Really. It's a harder process to compute also. So all the best, enjoy your course, and we can go out, we can continue our conversation.